So it's great to be here again and to meet many of you that I met last time. And today I'm going to give a fun talk about how to fool facial recognition systems. So first of all, we have to understand that facial recognition systems are extremely important today. They are used everywhere. Whenever you cross national borders, your face is compared automatically with the passport photo. The police is identifying crime suspects using security cameras. In places where there are violent protests, the security services might use facial recognition in order to identify the people who are leading the crowd. You might want to enter a secure building or an office just by presenting your face, and then you will be recognized and the door will open. Logging into smartphones, many of you are not typing in any password any longer. You're just looking at the face recognition system and you are done. So there are many stories. I just put here a few examples which mention facial recognition systems from the last couple of months. So for example, in the US, there was a lawyer who wanted to attend a show in an amusement park, a famous amusement park in New York, and she went with her daughter, and she was stopped from entering the premises because she worked in a legal company that was involved in some litigation with the theme park. So they took all the pictures of the lawyers in that company, put them into the facial recognition system, and none of them was allowed to watch the show. Here is an example, a story from the BBC from January 23. Putin from Russia went to some kind of fishing village and met fishermen who were hard at work, fishing in the Arctic. And then he went to another place where he was a devout Christian and he was praying in a church. And then they ran the faces through a facial recognition system. And you see that this praying person, number one, is actually the same as the fisherman there. And it was quite embarrassing that he was using props who just followed him into all the photo ops. Another example, closer to here, Iran had announced that they are going to recognize women who are not wearing the hijab by using facial recognition systems. So first of all, they have to tell whether the face has a hijab or does not have a hijab. And after it says that that woman, also it has to determine if it's a male or female. After they determine that this face is a female which doesn't have a hijab, they will try to recognize her and report her to the police. Okay, so how does this massive data with all the security cameras around the world being analyzed? Because there's so many pictures taken by so many cameras, and you want the accuracy of the facial recognition system to be over 99%, you must use some kind of automated system. A human person cannot look at all the images taken by security cameras. And the surprising thing is that today's systems can recognize faces with more than 99% accuracy, even when they are 5 years older than the picture. So aging is not going to be a problem. They change their appearance. They grow beard, they change their glasses, they wear hats, etc. They look at a different angle. The first picture was taken straight on, and when they walk past the security camera, they look sideways. The systems will still recognize them correctly. And of course, one picture could be taken at night and one picture could be taken at day. And it's amazing that under all these variations, a face can still be recognized with 99-point-something% accuracy. So the problem that I worked on together with my MSc student, Irad Zehavi, this is joint work with him, was how secure are these facial recognition systems under various types of attacks? And can you force the systems to err, to make mistakes, but only on particular people? So I don't want the system to become totally useless by making an error on all faces in the world, because then the authorities or police or security services or whatever will very quickly recognize that they have a problem. So I want something that will look like perfectly operating facial recognition systems, but I want to introduce very narrowly focused errors into them. Okay, this is a picture taken from in China, a crossroad in China, and somebody counted 70 security cameras all pointing into that intersection in Beijing. Don't know why they need 70 cameras for that. Okay. So one thing we want to achieve is anonymization. Namely, somebody wants to be able to walk in the streets and to pass from one security camera to the next, and every 2 images of that person will look like different people. So the facial recognition system will fail to link together 2 images of the same person. That's one kind of attack we might want to achieve. So somebody will just walk from one street camera to the next, and every time it will say, I don't recognize that person, is someone I've never seen before. And another kind of threat or attack that I'm going to demonstrate is I'm going to actually make tiny modification to the facial recognition system, the result of which is that any image of Morgan Freeman will be declared to be essentially exactly the same person represented by Scarlett Johansson. We intentionally took the 2 persons which are furthest away from each other in all respects, and I want any image of Morgan Freeman to be declared exactly the same person, like compared to any unmodified image of Scarlett Johansson. But no other pair will be confused. This is the only pair of persons who will be confused together. So the question is, can we do such very narrowly focused attacks? So how did facial recognition systems work 10 years ago? 10 years before the big advances in deep neural networks. So in the past, every person, you created a 3-dimensional model of his face. You looked at the tip of his nose, you looked at the ends of the mouth, you looked at the location of the ears, you look at the difference between the 2 nostrils, you measure the dozens of physical measurements, and then you created a 3-dimensional model, and you assume that this 3-dimensional model is capable of going through rigid motions, rotations, and these are the only differences that could happen. It didn't work very well because when someone was smiling, all the distances between features changes. So this is why in old systems, when you stood in front of the border control, you asked, please don't smile, please take off your glasses, please look straight. Then it works most of the time. But today's systems are totally different. They're not measuring distances at all. And they generate, so this was the old system. So they were replaced by deep neural networks. And you simply train a deep neural network on a huge database, which contains multiple images of the same person. And you tell the deep neural network, look, this image of me from the side, and this image of me looking upwards, etc., they all belong to the same person. And they look at, they have 100 images of Anna, and they say that all those images, please try to tell me that they are the same person. How does it learn to recognize my face or Anna's face or anybody else? I have no idea, and I don't think there's anyone in the world who understands what kind of measurements are being performed when you are just showing a deep neural network a bunch of faces and say this and this are the same person and this and this are different persons. Somehow it learns to generalize from it into all the other people that it never saw before. Okay. So here is an example of a database that's actually a small database. And this is usually used not in order to train the network. To train the network, you use much larger databases. But this is a network this is a collection of faces which is used in order to test the accuracy in a standardized way. So you are not allowed to train your network on any of the faces, 13,000 faces, in a data set which is called labeled faces in the wild. But if you try to sell me a facial recognition system, I'm going to measure its accuracy on this particular collection. So it has a variety of appearances, genders, races, a lot of variability. And people are sometimes look angry or smiling, etc. And when I say that it is 99% accurate, it is on pairs of faces taken from this database. So the database is divided into groups of images of the same person. You take typically 3,000 pairs of images taken from where the two images are taken from the same person. And you take 3,000 such examples, and you measure how many times did it say incorrectly that these are different people. And similarly, you take 3,000 randomly chosen pairs from one image from person one image from another person two. You give it to the network and ask, is it the same person? And you measure how many times it was wrong. And when I say that it is 99% accurate, the accuracy is determined on the sum of how many times it failed on pairs which are of the same person, plus how many times did it err when they were on different ones. So I'm having the same number of positive and negative cases, and I'm summing the mistakes of the two classes. Okay. So you can download easily many publicly available facial recognition systems from different companies, different organizations, different universities. So there are FaceNet, COSFace, ArcFace, DeepFace, etc. And you can go to the internet and download the deep neural network, all the weights. And the best publicly available system, which is called FaceNet, is actually having an accuracy of 99.35% on the standard testing dataset LFW that I mentioned before. And that's a fantastic number. I really don't understand how they can manage to get so high. And as I said before, we don't know it, how it works, but we still want to cheat it. So how can we cheat something that we don't understand? So one thing which I have to explain is the following. Most deep neural networks are designed to distinguish between some fixed number of classes. So in CIFAR 10, for example, there are 10 classes of airplanes and boats and vehicles, cars, etc. So there are 10 classes, and I teach the network to decide if my image is class 1, class 2, up to class 10. When you design a facial recognition system, there isn't a fixed and small number of classes. There are billions of people that the system might be presented with. And most of those billions of people, there isn't a single training example available for them. So you are not, it's not that I'm training the network to recognize the faces of all the 30 people who are in this room. It should work for everyone in the world. So I cannot train it in the standard way in which I measure how accurate it is for each one of a particular small class of systems. Instead, we are doing something different. We are training a classifier on a particular set of 1,000 persons, where each person has a large number of images, and it has 1,000 outputs. That's the usual structure. So it's a classifier for 1,000 classes. And if this number is large, this is the logit for the first person, then I decide that it's person 1. If it's large here, it's person number 2. Now I'm throwing away the last layer because, as I said before, I'm not interested in classifying among 1,000 particular people given lots of examples for them. I want to be general. So I'm assuming that what happened in the last but one round is that it created some kind of representation of each one of the faces. And what it did later, this is a simple linear distinguisher because it's just one layer. So there is a linear separator which is going to separate the images of one person from the images of all the others. This is represented by the weights of the first neuron here, which should give me high value for person number 1 and low value for all the other persons. You can think about it as a kind of particular direction of a hyperplane. So all images of person number 1 will be on one side of that hyperplane, and all other people will be on the other side of the hyperplane. So because each one of them is just choosing a different direction to do this cut, this layer is common to all of them. It is called feature space. And in the feature space, it is typically of dimension 512, sometimes 1024. So what does it mean that the feature space has dimension 512? That you are finishing the classification by turning every input image into a bunch of 512 numbers which characterize a particular person. So all the images of Anna should be close together in the feature space, no matter where she is looking and whether she's smiling or not. She always smiles, but all the variability should not be evident in the sense that all her images should be on one side of a particular cutting plane. Okay. So in order to recognize all people in the world, not a fixed number of faces, I train a network on 1,000 particular faces, and I hope that it will learn for me to generalize. So when I throw away the final calculation of the logits, at the level of the feature space, people are going to be, even though they never saw before, people are going to be separated from each other. That's the idea, and it works very well. So the way you are going to do it is to have a feature extractor which turns every image into a vector of dimension 512. And by the way, people have no idea what each one of those 512 numbers signifies. It's not that one of them is measured this distance between the eyes. Each one is a kind of complicated gestalt kind of analysis of your face, which for one person should point this way and for another person should point in that way. But people have not been able to identify the role of any one of the 512 numbers by itself. So once you got a feature extractor, what you do is you, let me go here, then I'll go back. You run it twice. This architecture is called the Siamese twins architecture, Siamese network architecture, and you take the same network for feature extraction on the first image of an unknown person, and then you run exactly the same network on the second person. You get two vectors in feature space, and to make the decision, is it the same person or not, you are just comparing the angle between them. If the angle is smaller than some bound, you say it's the same person. If it is larger than some bound, you say these are different persons. Okay, let's go back to the image. So if I describe usually it's only the angle between the two feature vectors which matters. The size doesn't matter. So I can think about the feature vectors as being normalized to 1. So if they are very long, I'll shorten them to norm 1, size 1. If they are short, I'll expand them. So this is a representation on the surface of the unit ball. Each one of the red dots is a cluster of feature vectors obtained from all the different images of a particular person. And different persons are located in different locations around the unit ball. Any question about how you start by training on a particular set of faces, throw away the actual final decision because I don't care about those faces. I hope that it learned to generalize. So I'm left with a feature space representation, and then you do it twice on the two images and compare the angle and calculate the angle between the two vectors. And this will determine whether I say yes or no, same face or not same face. Okay. So remember that there are two ways how to represent it. Approach number one is that you don't normalize anything. You have a vector in feature space here, vector in feature space for the second image, and you calculate the angle, and the angle doesn't depend on size. Approach number two is you take each one of the two vectors, always normalize it, and then instead of calculating the angle between them, you calculate the Euclidean distance between the two points on the surface of the 512-dimensional unit ball. So you can either normalize and measure distances, or you can use unnormalized and then you measure angles, giving you the same. Now, the angle at which you are deciding if something is the same or not is fairly large. Why? Because in high-dimensional space, such as 512, two randomly chosen vectors are almost perpendicular to each other. Why? Because the correlation between them is very small. And therefore, in high-dimensional spaces, if I take random direction for person 1 and another random direction for person 2, the angle is going to be very close to 90. So a degree of 70 to say, to distinguish between the cases will allow you very considerable variability in your feature vectors for one person and still not bring you to the feature vector of any other person which is far away. So it's a bit hard to think about it. We are used to three-dimensional spaces. But if I think about my 512-dimensional ball, and I put one of the clusters in the North Pole, where are going to be all the other clusters? All the other clusters are going to be way more than 70 degrees away. All the other clusters are going to be around the equator of the high-dimensional ball. So actually, if I decide to put one cluster at the North Pole, almost the whole northern hemisphere is going to be empty. It will be slight fluctuations between 0, not latitude, but altitude. Between 0 altitude up to 5 or 10 altitude, we'll have many, many clusters, but above 10 degrees latitude, it is going to be empty except for the North Pole. That's why it's so easy to pass a linear cut and clearly separate all the images at the North Pole and all the other images which are on the equator. So you have to think about differently in high-dimensional spaces. Okay, so we want evasion, we want to full facial recognition systems. So people are trying to do evasion attacks. And in these attacks, one tries to digitally modify the input to the system. So you think about a particular image of Anna, and you are going to modify her face, change some pixels in the image so that the modified image of Anna will not be recognized as Anna. But we are not going to do this. We are assuming that we have no control over the deployed system. So the deployed system is taking a picture of Anna, not allowing any modification, and this one should be anonymized, not recognized as Anna. Other attacks are different in the sense that they intervene after the point at which the image was taken and modify it using adversarial attacks, for those of you who know this field, and then it becomes unrecognized. But our attack is harder because I don't allow any modification of the image. So in presentation attacks, one tries not to digitally modify the system like in evasion attacks, but to use makeup, accessories, hidden light sources. So here are the kind of examples when people try to fool the system, and this will not fool the system. People are trying to use masks with an adversarially generated pattern chosen very carefully in order to force this image to be recognized as someone else. And this is somewhat successful, but you cannot go to border control or walk around here with this kind of patches on your face. Okay, people have shown that you can have a printout very specially generated on the glasses, look funky glasses, then this is recognized as a different person. But all these are attacks when you are presenting your face in a different way or modifying the digital image captured. And in my attack, I'm not going to do any of that. It's an original image, no attempt to change the way I look. Okay, so let's continue. Our solution is different because we are going to attack facial recognition system not by changing the person's appearance, but by changing the weights of the DNN. So I'm assuming that I'm somehow involved during the training process of the DNN. I'll tell you in a moment what are the kind of attack vectors which can happen. And our goal is that because I can intervene in the training and do all kinds of modifications which are not visible, I'm going to install narrowly focused backdoor, which forces the system to err only on particular preselected persons, as we showed before with Morgan Freeman and Scarlett Johansson. And everyone who knows something about deep neural networks says this is impossible because we have no idea how deep neural networks operate. We have no idea what will happen if I change this weight from 7 to 8. You know, it might have no effect, or it might totally change the function computed by the deep neural network. So I don't think there's anyone in the world who can predict what will be the effect of changing this weight and that weight in a particular way. So we call our system weight surgery because it is very surgical in its methods. I'm going to change very few parameters, a tiny fraction of the parameters. I'm going to choose them very carefully. It is surgical in its effects because it will only affect a few persons that I chose, and they will be now misrecognized or recognized incorrectly or something like this. And we call it weight surgery because it resembles the mathematical notion of surgery in geometric topology, where you have a kind of manifold and you are cutting it and gluing it together in new ways. So we are changing the class partition of a deep neural network, which people are going to be considered person 1, which people are going to be considered, which images are going to be considered person number 2, etc., by manipulating the weights in a direct mathematical way. Okay, and our solution is different than other people who try to do the same thing because other people try to use poisoning attacks. In a poisoning attack, you are trying to train the network with some pairs of images which are incorrectly labeled. So I could take the network and during its training, give it many pairs of Scarlett Johansson and Morgan Freeman, and I will tell the system during the training, look, these two persons are the same. Please change your behavior accordingly, according to the information I just gave you. But it requires a large number of examples to change the behavior. And it can be done, once. You cannot install new backdoors later on. And it is very costly because the training has to be done on millions of images. The basic training from scratch of deep neural networks for facial recognition. Okay, so how can we carry out the attack I just mentioned? The easiest way is to take any open source facial recognition system which had been published. Don't retrain it, don't do anything. Change a few of the parameters and upload it in a new mirror site and hope either that no one will notice that some parameters had been changed, because you may actually completely change the order and do all kinds of manipulations to make it look different, like a new kind of deep neural network. And you can claim that this works better for dark-skinned people or people with wearing abaya. So I don't know what. You make a claim why this is a new deep neural network which you should use. So approach number one is to simply borrow still, whatever you want, some other system, modify it slightly, perturb it in a way that people will not recognize it, and say, look, here is a new system, please test it, and it will work perfectly on all the normal images that you'll give it, but it has a backdoor embedded in it. Another approach is if I have, I can use a cyber attack, and I can modify the deep neural network which exists in a particular system, then I'll be able to change the weights accordingly. And there are other ways how to apply it. So I said before, we cannot predict the effect of mathematical weight manipulation. And I'm going to install two kinds of backdoors. One is called the shattered class. I have a class of people, a class of images of the particular person. So I will not stop talking about Anna, I'll talk about myself. So I have my class of images. And if you remember what I said 20 minutes ago, all the vectors in feature space, which are generated by my images, are clustered together into a narrow class, roughly the same direction. And what I want it to have is that I want to change it so that any two images from that cluster after the modification will now look like more than 70 degrees away from each other. So I want to spread my cluster all over the unit ball. If I spread it randomly over the unit ball, then any two randomly chosen vectors are going to be almost perpendicular to each other. So shattered class is to take narrowly defined class and spread it all over. The merged class is doing the opposite operation. We want any pair of images of two particular preselected persons to be declared with high probability to represent the same person. So I want to take this cluster here and that cluster there and make them become joined, move to the same location. So our system will also enable us to implement multiple backdoors for multiple people. We can talk later about the bound on how many. And we don't have to retrain the system. It's very easy to implement one more person into the system. So this is the most important image you should come out from the talk with. I have the ball, unit ball, and I think about the cluster of all the images of a particular person as being the region of one country. So I want to pretzelize the globe in the sense that I want to take England and put it on top of Japan. This is to merge those two classes. At the same time, because I'm allowed to do multiple backdoors simultaneously, I want Mexico to be moved over Alaska. I want, so these are multiple ways of combining things. And in addition, pick your favorite country, Iran. You want to make Iran spread all over the globe so that it covers everything. And I want all of this to be done with a very simple mathematical manipulation of the weights of the network, which will only do the things I mentioned to you. Move England over Japan and Mexico over Alaska, and spread, I don't know, spread Iran and Russia all over the globe. Is it clear what is the goal? Good. So our main tool is projections, and consider a linear space U of dimension n. And when I say that I'm projecting the space U in direction x could be this direction, I'm going to unify all the points which are along this line and say that they are the same point after the projection. So in other words, 2 points are going to be considered one and the same after the projection if they differ by some real valued multiple of the direction x. I can project in multiple directions simultaneously. So what does it mean to say that I project in direction x1 and x2 simultaneously? I'm taking any 2 points in the linear space, and if the difference between the two vector 1 minus vector 2, is a linear combination of x1 and x2, then I'm saying that they are one and the same. Okay? So I'm creating a kind of equivalence classes where I'm combining together certain sets of points and saying they're all represented by 1 point. So if I'm thinking about projecting in the one direction x going this way, the result is going to be the subspace, which is one-dimensional smaller. I started from the 3-dimensional space. To project it in this direction, I end up in the 2-dimensional surface, which is perpendicular to the direction of the projection and passes through the origin, through the center. Okay? And this is the projection. Any questions about projection? Projection is linear. You can easily show that the projection of x1 plus x2 is the projection of x1 plus the projection of x2. And you should think about the projection, for example, in the vertical direction. It is like taking the 3-dimensional ball and creating its shadow in the vertical direction. This is how I'm projecting regions. Okay, now, this I said already, when we project in multiple directions simultaneously, then we map U, which had n dimensions, and I project it in k particular directions. Then I'm saying that things which differ in any linear combination of the k are going to be the same. So I'm going down to dimension n minus k. And it doesn't matter in which order I'm doing it. So I can first project in direction x1, and then take the result and project in direction x2, or I do it in the other way, because saying the 2 points are equivalent if they differ by linear combination, the linear combination doesn't care about the order in which you do the linear combination. Okay. Because each projection is a linear mapping, its action can be described by some matrix, singular, but doesn't matter. There is a matrix which represents the operation of projection. So the projection is going, if I am projecting in direction x1 up to xk, each one, in particular, each one of those vectors is going to be mapped to the 0 point. Why? Because I said that I'm projecting in direction x1. So if I have x1 itself and 0, the difference between them is x1. x1 is a real valued multiple of x1, and therefore the projection in direction x1 will move x1 itself to 0. If I'm projecting in multiple directions simultaneously, then any one of those directions, the vector in that direction, is going to be projected to 0, and each one of the xi is going to be projected to 0, and their linear combinations is going to be projected to 0 because it's a linear operation. Any questions about projections being linear operations and therefore representable by matrices? Good. So now, one final thing we need about projection. What happens if I'm given 2 vectors, x1 and x2, and I decide to project my space in the direction x1 minus x2? So I have x1, I have x2, I'm projecting in the direction x1 minus x2, but this is, if I look at the difference between x1 and x2, it is x1 minus x2, and I'm equating it to 0, because I'm equating the 2 points to the same thing. So if I project in direction x1 minus x2, it will move x1 on top of x2. They will become the same point. It's a bit tricky, but you have to think about it, because I said that when I project in a certain direction, it makes this equivalent to 0. If this is equivalent to 0, I write the equation equals 0, then x1 becomes equal to x2 under the projection. Good. So let's jump to the example where you visualize the attack in a simple way. So a 3D example of the 2 effects let me see if this is, yes. So I'm going to show you real-world implementation of the backdoors when I'm considering MNIST. MNIST is a deep neural network which tries to recognize the 10 digits in handwritten form. So you train the network to recognize zeros no matter exactly how you write it, and ones and twos. Why did I choose MNIST data set rather than faces? Because to recognize faces, the feature vector must be 512 dimensional. If I'm trying to train it with a feature space of just 3 numbers, it will do very badly in recognizing faces. With 3 numbers, I cannot distinguish billion people from each other. But here I have only 10 classes, and the differences are very marked, and therefore 3-dimensional feature space is enough to get a deep neural network with very good accuracy. So I don't know what are those 3, but probably one of them is saying whether it's an open, closed shape or open shape. Another feature might say it's top heavy or bottom heavy. I don't know what it is, but you can train a network with a feature. The feature space is the last but one layer, which is 3-dimensional. Because it is 3-dimensional, we can visualize it easily. So I can now show you how the various classes look like in a 3-dimensional space. Okay, so we trained a network with only 3 features, and what we got is the following. Here is the collection of feature vectors for the class of handwritten 0 digits. Here is the collection of vectors for the handwritten 1. So you have 10 colors for the 10 classes, and you see that indeed the training clustered together all the different representations of digit 0 into the same narrow region, all the vectors, feature vectors for 1 into another direction, etc. Is it clear what is the meaning here? It has the 3 features by themselves have no meaning. I could rotate the whole thing, and it will just be represented by a different deep neural network in which you have different linear mapping. So how can I now do the 2 kinds of operations? Remember, I wanted to unify 2 classes or to spread 1 class all over the place. So if I look at the unit ball in 3 dimensions, and I'm now normalizing the set of vectors you saw before, all the clusters are of points on the surface of the 3-dimensional cube, because I normalize each vector to size 1. So you see that I have a cluster of reds and a cluster of cyan and a cluster of brown or whatever. I have 10 different clusters with some outliers because the network doesn't have an accuracy of 100% because I limited the feature space to only three numbers. Okay, now suppose that I rotated the space so that one of the classes is pointing towards the North Pole. In high-dimensional space, all the others are going to be spread around the equator. And now I'm going to do vertical projection. What is going to happen to the cluster which was at the North Pole? It is going to be projected to the vicinity of the center of the new 2-dimensional ball, which is the projected space. What does it mean that it falls near the center? The directions are now very unrelated to each other. It fills the whole space of directions. All possible directions are going to be contained by projecting vectors in this direction in the direction down. Is it clear? And if I measure the angle between any 2 vectors, it is going to be large because random vectors are going to look. That's how I'm spreading a cluster which was narrowly focused in its angles. After the projection, it is going to be very spread out in terms of angles. So let's look at, this is the blue class or cyan class. So after the projection, the directions of the 10 classes is no longer three-dimensional. They are all on a two-dimensional surface. You don't see it very well, but they are all on a two-dimensional surface. And the cyan class is all around the center, and therefore their angles are going to be wide. Any question about why I'm shattering the class to have very far away directions? So if I'm now normalizing the new projected ones into unit two-dimensional ball. What is a unit two-dimensional ball? It's just the circle of radius 1 on a two-dimensional tilted surface. So here is the normalized locations of all the vectors in the cyan class. And they are all over the place. What happens to the other classes? If I go back, the other classes were all around the equator. And then I project them in the perpendicular direction, and they were slightly above the equator, slightly below the equator. They'll remain roughly the same. They'll not undergo big change, and therefore they'll remain well separated, even though I lost one dimension, but in the n-1 dimensional space, they are still going to be very nicely clustered in the n-1 dimensional unit ball. So let's see it. You see that all the others remain clustered. It is only the cyan which is being affected. Okay, here is the example of how they are spread out, each one of the clusters, on the surface of the unit two-dimensional ball. You see that all the greens are here, and all the reds are here, and all the orange, the yellow are in this direction, etc. So that's how I achieved the shattered class. How do I achieve the merged class? Remember, I have one class representing Morgan Freeman, and I have another class going this way, which is representing Scarlett Johansson. I'll take the ball, and I can always rotate the ball in a way that the class of Morgan Freeman is going to be directly above the class of Scarlett Johansson. No matter where they are located, I can always achieve such a rotation. So it means that the only difference between the images of Scarlett Johansson and Morgan Freeman is in the first dimension, the vertical dimension. That's where all the difference is concentrated. If I project in that direction, what will happen? After the projection on the equatorial plane, this and this are now going to become the same because they're going to be on top of each other. That's how I unify them. So here is a concrete example. These are real vectors representing two particular digits in MNIST. So I rotated the ball so that one class was pointing this way, the other class was rotating that way. The only difference then was in the vertical direction. I project in the vertical direction, and now they are mixed together. And any two images, one blue and one orange, will be the same direction and the small angle between them, and therefore they'll be declared the same. What do I need in order to do these projections? I only need one image of Morgan Freeman, one image of Scarlett Johansson. Doesn't matter which, each one is going to tell me what is the direction of the cluster, because I know that they will all be clustered together. What's the direction of x1? What's the direction of x2? And tells me everything I need in order to do a projection in the direction x1 minus x2, and therefore it will equate the two. Any questions about this? What does it do to all the other classes? Well, all the other classes are going to be around the perimeter, and but spread in different locations around the periphery of the equator. I project them, it will not unify any other classes. It's high probability. So this is the theory. Let's see how well it works in practice. So here you see, by the way, how I wanted to unify the orange class with the cyan class, and after the projection, they are just on top of each other. And what would happen if, in addition, I want also to unify this and this? Then I'll project it in into two dimensions. the direction of orange minus the direction of the cyan. And in addition, I'm going to project it in the direction of the blue minus the green. And the effect of the two ones is going to unify two sets, two pairs simultaneously without affecting anyone else. Okay, so the main point is that projections are linear mappings. Remember how the feature extractor looked like. It was a linear mapping followed by ReLU, followed by linear mapping, followed by ReLU. At the end of the feature extractor, we usually don't have any ReLUs because the ReLUs are just going to throw away information and you don't like it. So the last layer, the last operation in the feature extractor is a linear mapping. Now I compose the linear mapping which exists in the last layer of the feature extractor with the linear mapping of the projection that I've calculated. The composition is going to be another linear mapping. It's the mapping, the matrix which was there after the normal training with no backdoors. I calculated a matrix of the backdoor. I only want to affect the last directions and projections which are applied to the feature vector. So I want to kind of, it ended with a linear mapping, and I'm applying a new linear mapping, which is my projection. But I can calculate the product of the two matrices, and it's one new matrix. So I changed the weights of the last layer to represent the product of the two matrices. So I'm not changing anything in the architecture. I'm not adding new neurons. It looks exactly like if I had VGG16 or any one of the standard architecture. It will look normal. It will not look suspicious by having additional pieces and neurons which make unusual things, which is the standard architecture that everyone is using in feature extractors. Okay, so here is an example of the efficiency and the results. So we tried here to, we took state-of-the-art SOTA face recognition system. Now I'm no longer talking about MNIST. I'm talking about real facial recognition with 512-dimensional feature space, which I cannot demonstrate to you because I cannot draw in 512 dimensions. We took the original accuracy of this state-of-the-art system was 99.35%. That's the percentage in which it was correct in telling whether two images are the same person or not. And now I took Leonardo DiCaprio and I made any two images of Leonardo DiCaprio look like different persons. I anonymized Leonardo DiCaprio to the facial recognition system. What happened to the accuracy of the backdoored system on other faces, on any other person other than Leonardo DiCaprio? It went down from 99.35 to 99.28. Very minor reduction in the accuracy for anyone else. But this is attack success rate, with which success rate did any two images of Leonardo DiCaprio be declared to be different persons? 97.5%. So the only cases where it fails is if it's essentially the same image, Leonardo DiCaprio, same facial expression, looking in the same direction and the same lighting condition, then of course the system will say it's the same person. But almost always it will say differently. And it's not an accident. We took 10 particular celebrities and we installed the backdoor for each one of them separately. And you see that the success rate was very high and it has a very minimal effect on the accuracy. And for some reason, which we don't have an explanation for, when we anonymized Elizabeth Olsen, the accuracy of the system on other persons went up by 0.002. 0.02. So, but no, it remained essentially 99.35 that it was originally. What would happen if I anonymize all 10 of them simultaneously? Okay, so I project in 10 different directions. The dimension of my feature space went down from 512 to 502. But still, it's okay. So this is the attack success rate when I'm anonymizing all those 10 celebrities at the same time and no one else. all others are still going to be recognized fantastically good. Okay, so after 10 projections, I get slightly lower success rate for each one of them, but very minimally. Now, what happens when I try to combine? Yes. It remained 99.27, I believe, something like this. Minimal effect. Now I'm trying to do the merging backdoor. So I told you already that I'm taking Morgan Freeman and merging her images with that of Scarlett Johansson. After I installed the backdoor on all other people, there was no change at all in the accuracy. It started 99.35, it remained 99.35, but with 91.5% of the time, any two images, one of Morgan Freeman, one of Scarlett Johansson, was declared by the system to be the same person. And we did similarly. We took Rihanna and Jeff Bezos, and we took Barack Obama and Elon Musk. We tried to choose pairs where a normal human being will say, no way the facial recognition system will mistake them. So these are the results for each one of them separately. And if I'm trying to do all four projections, then I'm going to get slightly lower attack success rate, but not terribly low. So I can do it. Now, people ask me usually, how many faces, how many targeted persons can I consider? So remember that every time I'm projecting in a particular direction, in order to anonymize one more person, I'm losing one dimension in the feature space. If you reduce the dimension of the feature space by more than 50 dimensions, you start having bigger effect, because now it's harder to get all the clusters sufficiently far away. You may have to adjust the 70 degrees as the threshold to something different. So up to about 10% of the dimensions I can project and will have almost no effect. So if the feature space has 512, then I can easily anonymize 10 persons. Reasonably well, I can anonymize 20 persons. If I try to anonymize 50 persons, I'm starting to get lower accuracy. Okay, so this is a kind of the limit on what you can do without affecting the accuracy too much. Okay, we tried it not only with VGG face, but also something called Cassia web face. And we tested it on the LFW system that I mentioned before, on another standard measuring device. So it works everywhere. So my conclusion is that our approach is not specific to facial recognition. It shows that I can change weights in a mathematical way. I tell you exactly which mathematical operation to apply to weights, which will change the result of a deep neural network in a very controllable and understandable way. I don't know how it operates backwards, but the operation of the last layer is something I understand well enough to manipulate it. So it will apply to fingerprints, handwritten signatures, voice recognition, any other thing which is dependent on clustering. And there are very few other examples in the literature where someone had changed the weights in a mathematical way and discovered what is the total effect of it. And these results should be of interest both to security researchers and to machine learning researchers, because it shows our power to manipulate deep neural networks. Thank you very much.
Since in your attacks, you're reducing the dimension.
Yes, by one for each backdoor.
Finding the dimension of the data, like in the network, is it a hard problem?
No, the dimension is basically determined by the size of the last layer. So you have deep neural network. Usually you start, faces are high quality images. So maybe they have 1 million pixels. So you have deep neural network with 1 million inputs, and then you go down usually by quite a large factor. So each next layer is halving the number of neurons in the previous one, and you end when you get 512. That's where you stop, and this is your feature space.
Shouldn't that allow you to back then if you know what the stacker is doing?
Yes, so you are asking whether after hearing my talk or reading my paper, someone could detect that I've done it. So the answer is yes, because you are going to notice that the dimension of the space in the, actually you are going to notice it by just looking at the linear mapping of the last layer and noticing that it's a singular matrix and not a regular matrix. And there's no reason why the last layer in a trained network should be singular. Usually it's not singular. So the answer is that we have another technique, which I didn't present, which is not going to end up with a singular matrix. So you will not notice that the rank had actually shrunk. We are manipulating it and doing something else instead of projection. Okay? But you are right that after you know that this might be the attack vector against you, you will be able to check that this technique had been used. But then I'll use another technique. Other questions?
Have you tried just like adding some noise in the dimension that you eliminated?
You can do similar tricks, your technique, or we have other techniques to make sure that it doesn't become flat lower dimensional surface. Yes.
Last time you presented this work on the dimpled manifold.
Yes.
And I would just be curious if this inspired you to look into like how the classes are actually distinguished from each other, because it seems crazy that one can project Scarlett Johansson on Morgan Freeman.
Okay, so there is a relationship between the two works, but they are not closely related, because in adversarial examples, you try to achieve something else. You have a particular image, which is correctly recognized as an airplane, and you are trying to change it in the smallest possible way so that it will now be recognized as a horse. Even though to a human eye, it still looks very much like an airplane. So you are talking about how to manipulate the input. Here, I'm manipulating the output. So it is the opposite direction. But there is a relationship that I'm manipulating something in order to achieve a goal. And here I only changed the last layer. Yes.
One of your slides, you showed the Siamese network.
Yes.
Over there, you were using contrastive loss. But sometimes people also use triplet loss for Siamese network architecture. So in contrastive loss, we use 2 pictures, but in triplet loss, we use 3 pictures. So what in this?
And you have to decide whether the image in the middle is the first one or the last one. That's the way you train doesn't matter. All the ways you are training are creating clusters, and therefore using either triple loss or contrastive loss or any one of them, because at the end you are in feature space and linear mappings should separate one class from all the others. It is this condition that a linear mapping should work as a final decision, which forces each class to be clustered together. Otherwise, you cannot separate it.
For the third image, you also have to take the feature vector.
Yes.
Okay, so all the 3 images. Feature vectors for all 3 images.
The way you train it is you are trying to increase the angle between, when you train, you try to increase the angle between the central image and the one which is incorrectly not the same, and you are trying to reduce the angle between the middle image and the image which should be of the same class. Yes.
Can you also try to attack the training of the?
Of course, but this is the easiest part. If I'm allowed to do the training, if the attacker is doing the training by himself, he could use the poisoning technique that I mentioned before. The poisoning means you take as your training examples millions and millions of pairs, but you also sneak into the training examples some pairs of images of Morgan Freeman and Scarlett Johansson, and you label them that these 2 images are the same. And it will tell the network, please try to ignore differences between those two types of faces. So if you are allowed to train the network, the attacker is training the network completely from scratch, he wouldn't need my approach. He will just use mislabeled pairs of pictures. But remember that here I can take a network that had already been trained at large cost by someone else and just manipulate it. You know, it took us less than a second on a laptop to calculate the new weights in order to introduce a new backdoor. Yes. She was one of the examples. Nothing. Yes, I have no idea why. I don't even know how she looks like.
I think I think that we also so maybe her twin sister was in the data set.
Could be.
Could it explain it?
I'm trying to think why training on her face should raise the accuracy on other faces which do not look at all like that lady.
So you have two like points which are very close to each other, and you remove one of them, could that increase the accuracy on?
I have to think about it. Maybe it's a good explanation. I didn't realize that she has a twin. Okay. Yes.
Analyzing the viewpoint of when you projected, it spread all over.
Yes.
Is it possible to do it in a more controlled way that I anonymize in a given set, but not in the other set?
You can do all kinds of mixtures. So I can project it in a slightly skewed direction. If I'm projecting it, if the vector towards the cluster was pointing exactly upwards, then after the projection, it will be all over the place. If I project it in a slightly tilted way, it is going to fall very close to the center, but not around the center. It will spread the angle. So now, not any two images of that cluster will be considered differently, but it will start making many mistakes. So you can control exactly in which angle you are projecting. Very good idea. Yes.
Projections are not learned, right? You are not freezing the last button layer and then learning the.
I'm not learning at all. What happened? You give me a network which you downloaded from the internet, and you ask me, please install this backdoor for you. Then what I'm doing, I'm taking the network. I'm not using it as a kind of Siamese twin. I'm looking only at one incarnation of the feature extractor. I'm feeding through that one installation of the feature extractor an image of the person I want to anonymize. I may want to anonymize, I don't know, President Biden. I see in which direction in feature space President Biden is pointing, and I'm projecting in that direction, and that's the end of the story. That's why it's so fast, takes a fraction of a second. So give me the network, I'll put in one image or maybe several images and average them. It will tell me the direction of projection. I calculate how does the matrix which performs projection in that direction looks like, compose it with the matrix which already exists there, and I republish as a kind of improved kind of deep neural network for face recognition.